So this is the last lecture in the electric, gravitational, and magnetic fields unit. It's on motion of charged particles in magnetic fields, and it's section 8.4 from your textbook. So basically what we're looking at now is we looked at what happens when we have a moving charge in an electric field and the magnetic force on that charge. What we're going to look at in this case is if we have a charged particle that's moving in an electric field, we can actually use our knowledge of physics to determine the mass of that charged particle. So I'll get into that. Now this slide here introduces us to the idea of a mass spectrometer. And it says atoms and molecules are the building blocks of our universe. But these are really, really small particles. So how do scientists study these particles? One thing we use is a mass spectrometer. These mass spectrometers are able to define the elemental composition of a sample of molecules, or a sample or molecules. So to determine the masses of particles and to reveal the chemical structures of molecules. Now how does this work exactly? So let me just see how they describe it here. Actually, I'll describe it first before we get into this, just because I think it might help you understand. So with a mass spectrometer, basically what we do is we send a charged particle through a magnetic field. And we know that any charged particle that's moving in an electric field will experience a magnetic force. We can set the magnetic field so that the force is consistent. What will happen is masses that are, or particles that are more massive will be deflected less than masses that are less massive. If we can set the force to a constant value, so imagine this as a, imagine a particle is moving. The mass spectrometer applies a force of, say, 1.0 times 10 to the negative 9 newtons of force on that. That particle will be deflected by that force. And if the particle has a very small mass, it will be deflected more than a particle that has a larger mass. So this idea of how much it deflects helps us determine what the mass is. The other issue is that we have charged particles that are either positively charged or negatively charged. So the direction it deflects will also help us determine what the charge is. So now let's read through these slides here, because we're going to talk about the mass spectrometer, and we'll introduce an equation for this. In this mass spectrometer, you can see it says acceleration on your left side. There is you can imagine that on your left being something shooting a charged particle into the magnetic field. And the magnetic field is what we call the velocity selector. So it's directed into the page. Our charged particle is moving to the right. The faster ions will deflect up. The slower ions will deflect down. So this velocity selector is a device quite often associated with a parallel plate particle accelerator. A beam of particles having different velocities as a result of carrying different charges is filtered so that only those particles with the same velocity continue. So basically, this filters out the particles so that we have only one velocity particle coming through. This helps us come up with a consistent force, because if we look at our Fm equation, the magnetic force equation is Fm equals QVB. Well, we've set B by setting the magnetic field. We have set Q by shooting the same type of particles out. The velocity selector allows us to only allow particles of the same velocity to go through. So now that we've made QVB constant, we've made FM constant, and this will help us find our mass. So then ions of the selected speed enter another magnetic field, and this magnetic field will have some deflection. If we have a lower mass particle, it will deflect less. A higher mass particle will deflect more. And you can notice that the deflection is circular, so there's a centripetal force that's causing this. So we can now relate this back to our Fc. If you remember, Fc equals mv squared over r. Fc equals Fm, and Fm equals QVB. So we can rearrange that equation. It becomes QVB equals mv squared over r. And rearranging that, we get the mass spectrometer equation, which you'll see coming up. Actually, it's right here. I just realized this is kind of shown on the wrong page. Apologies. Let me just go back and take this out. Okay. So we can see that rearrangement here that I was mentioning. So Fc equals Fm. Fc is mv squared over r. Fm is QVB. We could rearrange. We get m equals rqbv, over v. And this is the slide I'd like you to copy down. So this whole lecture is basically about this one application of magnetic fields. So we can use this then to determine the mass of the particles that we're shooting into the field. So here's a question. It says we have a positive ion. It has a charge of 3.2 times 10 to the negative 19. It travels perpendicularly through a magnetic field with a strength of 0.1 Tesla. The speed has been selected to be 3 times 10 to the 5 meters per second. The radius of the circular path of the ion is 6.26 centimeters. What is the mass of the ion? So this becomes m equals rqb over v, and our radius was in centimeters, so I just want to make sure I get that right. So our radius is 0.0626. Our q is 3.2 times 10 to the negative 19. Our b is 0.10, and our v is 3.0 times 10 to the 5. So looking at these, we have 3 significant digits here, but there's 2, 2, and 2. So our answer has to be given with 2 significant digits. And after I calculate this, I'll do it quickly here. 0.0626 times 3.2 times 10 to the power of negative 19 times 0.1 divided by 3 and 10 to the power of 5. I get 6.7, so I have to round to 2, times 10 to the negative 27 kilograms. Now what I could do, I know this is an ion, but I don't know what type of ion it is. Using my knowledge of chemistry, I can then go back and try to figure out from the masses, what is this ion? Here's another question. It says that we have an electron, so we know the mass of an electron. And we're asked to predict the radius that the electron will travel. So this is just a simple rearranging of the equation. So for this one, to rearrange this equation for r, it will be r equals mv over qb. And in this case, my m is 9.109 times 10 to the negative 31, because that's the mass of an electron. My v is 3.4 times 10 to the 5. My q is 1.6 times 10 to the negative 19. And my b is 6.8 times 10 to the negative 5. So substituting this into the equation, I end up with 9.109 times 10 to the power of negative 31 times 3.4 times 10 to the power of 5 divided by 1.6 divided by 10 to the power of negative 19 divided by 6.8 divided by 10 to the power of negative 5. So I end up with two significant digits again, so it's 0.028 meters. So a bubble chamber is another type of mass spectrometer. So this is a device used to study the trajectories of elementary particles such as electrons and protons. The diagram shows the trajectories of some typical particles, one of which is indicated by this white arrow. So you can see that they kind of curve around. They form these sort of bubble structures. So the question here that's asked is, is this particle positive or negative? And our magnetic field is directed into the page. So if you imagine, point your index finger at this picture and move your thumb in the direction, your thumb in the direction of the of a positive particle, and because the particle is moving in that direction, the positive direction, it must be positive. So to describe how the trajectory changes when the mass is decreased by a factor of 10. Going back to our equation, you can kind of do this on your own. The mass spectrometer equation, if we decrease 10 by 10, then we decrease the mass by 10 as well. Sorry, if we decrease the mass by 10, we decrease the trajectory by 10 as well. And the same thing happened if we increase the charge of the particle by 3, then the radius would decrease, because the radius is inversely proportional to the charge, because they're on the same side of the equation and their products on the same side of the equation. So we're going to finish off this lecture with a talk about field theory to kind of cover everything about this unit, magnetic, gravitational, and electric fields. So we associate the term force with a physical action. So we always think of forces as the bat hits the ball, that's a force. I push something with my hands, that's a force. But really what happens is it's a field of force. So your hand, there's a bunch of little force vectors when you push something with your hand. So that's something else to consider, because it's really this interaction of these individual atoms in our hand with the individual atoms of the thing we're pushing. So there's this whole field of force that happens. So how do we create an understanding of gravitational, electric, and magnetic fields? Field theory is the scientific model that describes force in terms of entities. We call these entities fields, and they exist at every point in space. Field theory can be applied and explain the minute interactions of subatomic particles, as well as describe the motion of galaxies throughout the universe. So studying gravitational, electric, and magnetic forces has revealed differences and similarities between these forces and their respective fields. The electric and magnetic fields have stronger effect on the motion of subatomic particles, such as protons and electrons, but the gravitational field has a stronger effect on larger objects, such as planets and galaxies. So despite these similarities and differences, field theory states that electric, magnetic, and magnetic fields are more closely related to one another than they are to the gravitational field. In fact, the electric and magnetic fields are thought to be different aspects of a single field, which we call the electromagnetic field. They are used in conjunction with one another in a multitude of innovative technologies ranging from particle accelerators to artificial hearts. And we're going to get into this more in Unit 4, when we talk, which is going to focus more on electromagnetic radiation. So I'd like you to copy this down. Field theory, it states that if an object experiences a specific type of force over a continuous range of positions, that a field exists in that area, and it can be applied and explain the minute interactions of subatomic particles, as well as describing the motions of galaxies throughout the universe. And with that, we're going to end Unit 3.